There's one structure which has endured since ancient times, an essential element of buildings and bridges alike, the arch. The arch's strength lies in its shape, and over the years it has proved one of the most reliable forms of construction known to man. In this programme, we travel to Cologne Cathedral to explore the Gothic arch, and to Hamburg to see how, using modern materials, arches have evolved. But we start with the civilization who were the first to really exploit the concept of the arch on a large scale, the Romans. This is the magnificent Pont du Gard near Nîmes in the south of France. Upon seeing the bridge, the 18th century philosopher Jean-Jacques Rousseau said he felt lost like an insect in the immensity of the work. It formed part of an aqueduct 50 kilometers long, which supplied water to the Roman town of Nemesis, now known as Nîmes. It's the highest bridge the Romans ever built. It's an incredibly striking structure, 48 meters high, with 3 tiers of arches to carry the aqueduct at the top across the river. These are classic semicircular Roman arches. In all, there are 6 across the bottom level, 11 in the middle, and 35 across the top. The longest span is 24.5 meters, among the longest spans of any bridges built by the Romans. The aqueduct was thought to have been built during the 1st century AD and was needed to cross the river Gard, a tributary of the Rhône. With arches, the Romans discovered a simple and effective method of bridging space. But the valley was much too wide to be crossed by a single span, so the Romans solved this problem in the highly practical way that characterizes many of their major building works. The aqueduct simply consists of lots of arches which together bridge the valley. You can see that a footbridge has been built next to the aqueduct, almost doubling its width. This was done in 1747, and its stone arches exactly echo the originals. In fact, it's quite a sympathetic add-on, and it doesn't detract from what we're here to look at. The arch itself is made up of these stones here. They're all slightly wedge-shaped, and together they form a semicircle from this pier to that one over there. Stone cracks easily when it's pulled apart, but when it's compressed, it's immensely strong. The arch works because each stone pushes against its neighbour, and the weight is carried outwards and down. When the forces reach the end of the arch, they're taken down the pier to the ground. The thickness of the stones making up the arch are crucial to whether it stands or not. These are over 1 metre thick, approximately 1/20th of the span of the arch. The Romans never made sophisticated calculations, but they knew from experience that if the stones were any thinner for an arch of this size, the arch would be at risk of collapsing. Once built, an arch is incredibly strong. It can support a lot of additional load on top, but the weight has to be spread across it, and that's what these solid parts are for, called spandrels. The spandrels are not part of the arch, but they just transfer the loads from above into it. So it doesn't matter what they're made of, and behind this stone facing is just compacted rubble filler. The Romans were expert builders, and the Pont du Gard must be one of their greatest achievements, especially when you consider that the technology available to them was limited. The arches were built on wooden scaffolding, which carried the weight of the stones until the last stone was dropped in at the top, the keystone. Once the scaffolding was knocked away, the arch would stand, hopefully. Although these arches are among the largest the Romans ever built, their span was restricted by their equipment. The stones were lifted up into position using wooden cranes worked by teams of slaves. the biggest crane the Romans had could only reach around 15 meters. So if you had one crane on each side, the biggest arch you could build was less than 30 meters. At the top, the water channel is just 1.25 meters wide and over 1 meter deep. It's the only part of the aqueduct that uses mortar, needed for waterproofing. Originally, it would have had a stone roof, but much of this is now missing. Looking along the aqueduct, you can see that it's developed a curve towards the upstream side. This is because, over the centuries, undermining of the piers has caused the bridge to lean over ever so slightly. But masonry is extremely robust, and it would take much greater movements than these to cause it to actually collapse. The Romans' major contribution was in the construction process, the organisation and techniques which were used, rather than the development of new design concepts. The Roman engineers learnt from experience, setting out their arches using geometrical rules. This system was highly effective, perfectly suited to their needs, and the Pont du Gard is the finest expression of this. The Pont du Gard is a celebrated object of beauty, a remarkable piece in the huge jigsaw of Roman engineering. They were the first civilization to understand the value of the arch, and their use of it as a fundamental building block in much of their construction is an enduring part of their legacy. This aqueduct and the other structures they created across Europe are a lasting monument to their skills. The fact that bridges such as the Pont du Gard still stand is also a testament to the strength of the arch. Once built, they will pretty much stand forever, or until the stone finally weathers away. But over the centuries, changes in building styles have forced the arch to evolve. Nearly 1,000 years later, in a new phase of monumental construction, the arch found a major new expression. The 12th and 13th centuries in Europe saw an extraordinary explosion of architecture and engineering, driven by merchant wealth and religious fervour. This was the High Gothic Age. Many of our greatest cathedrals date from this period, including this one, the imposing Cologne Cathedral in Germany. It has a highly decorative, even extravagant exterior, but all this decoration is actually concealing quite a simple structure of arches and vaults, which owes much to the Romans. Like the Pont du Gard, the structure of Cologne Cathedral is entirely based on arches, but the crucial difference here is that the round arch has been replaced with a pointed arch. This was a vital development which allowed a different form of building altogether, a building which was light and spacious, but above all, which was high. All this was achieved because the pointed Gothic arch carries the weight more directly to the ground. It's a much more efficient shape, so it can be much thinner. In addition, the symmetry of the arched vaults and the clean vertical lines of the piers give Cologne Cathedral its particular elegance. Cologne Cathedral has its roots in the great French cathedrals of Notre Dame and Amiens. The choir here at the East End was started in 1248, but it took another 600 years for the towers at the West End to be finished. In reality, work on this building never stops. There's a local saying, which loosely translates as, "When the cathedral is finished, the world will end." In the great cathedral building boom, new skills and techniques evolved. Stained glass windows and high arched stone ceilings grew ever wider and more magnificent as towns and cities tried to outdo their neighbours. That these structures have lasted nearly 1,000 years can be attributed to the knowledge and experience of the stonemasons who built them. Stone was shipped down the Rhine from the Drachenfels, 40 kilometres upriver. The master mason supervised the whole construction, combining the modern role of engineer and architect and organising the teams of professional craftsmen on site. They were highly sought-after men. Cologne Cathedral was laid out by Master Gerhardt, who had visited France, where he studied the techniques used in building the French cathedrals. By the time of his death in 1260, the cathedral was beginning to take shape. Although many master masons followed Gerhardt, it was his vision which we see in the layout of the cathedral. The rules of proportion used in the design were originally developed by the Greeks and were handed down from generation to generation in the Masonic lodges. It wasn't until much later that people began to understand, in structural terms, why they worked. What the Masons knew was that a building built strictly according to their geometric rules would stand up. But building this high created new challenges. The weight of the roof on the tall vertical piers pushes them outwards, so the piers have to be supported in some way from the outside. Because the cathedral is so much narrower at the top than at ground level, where you can see all the extra space in the aisles, the supports for the roof have to span right over the lower level. So a new development was needed, a Gothic invention, the flying buttress. All around the perimeter of the cathedral, the upper levels are supported using these flying buttresses. In fact, these are flat arches, and they work very effectively. The force outwards is concentrated where the roof and the vault meet the pier, here. The force is carried down the arch, like this, and the weight of the buttress directs the force down to the ground and stops it toppling outwards. The pinnacle is also a nice detail. It adds weight to the top of the buttress to stop the arch breaking it off. The cathedral has survived through some difficult times. There was damage during the Second World War when 10 vaults in the nave and north transept collapsed. One bomb damaged the tower so badly that it had to be bricked up, and it has been left deliberately in this condition as a reminder of those years. There's currently a major program of restoration underway. Many of the pinnacles have been repaired, including that one, the top of which fell off in an earthquake in 1992. There's also a plan to protect and clean the whole building, but without changing its overall appearance. Over time, pollution has turned the cathedral almost black, and this has given it an almost foreboding appearance. Nevertheless, Cologne Cathedral still remains remarkable in its details and awe-inspiring in its scale. With just simple hand tools, wheelbarrows and winches, the builders of these Gothic cathedrals realized the most complex industrial projects in Europe since Roman times. Their organization of the site itself into teams of paid professionals rather than slaves was fundamental to their success. But for me, it's what they achieved technically in a pre-scientific age that's so extraordinary. Because of their strength, steel and concrete have now largely replaced stone as a building medium. But where great spans are needed, the arch is still an extremely attractive solution. This is the jumbo shed built for Lufthansa Technik, the engineering wing of the German airline. It takes 3 planes, including 2 747s, and is one of the biggest aircraft hangars in the world. Forming the heart of a base here which employs over 5,000 people, it was opened in August 1992 at a cost of 172 million marks, over 60 million pounds. The design of this enormous hangar posed some real engineering challenges. Lufthansa wanted to be able to open the whole of the front of the building to get the planes in and out easily. Secondly, the height of the building is restricted by airport regulation. This meant the roof had to be supported in a rather special way. Instead of columns underneath, 2 huge steel arches hold up the front of the roof. The roof frame is suspended from the arches by hangers, rather like the deck of a suspension bridge. The arches are positioned towards the front of the building because the doors can't carry any weight, but the back of the building is held up on ordinary columns. The arches span 180 meters from one side of the building to the other. They sit on 4 A-shaped supports, 2 at either end of the building, and the arches get additional stability by leaning together and being joined with struts. Just crossing the threshold through these huge doors and into this giant hangar, it's quite spectacular. A jumbo jet is 7 stories high, but it's dwarfed by the height of this roof. This one's covered in platforms and machinery, spaces for men to work. This is where the 3rd plane goes, right here. The hangar is used to service primarily jumbo jets. Working 18 hours a day, it takes 7 weeks to totally refit a plane, and it costs 3 to 4 million pounds, not counting the engines or the paintwork. The construction of the building was quite ingenious. The whole roof, with the arches, was built out here on the ground, while the foundations were laid on site, saving time and money. The roof was then slid on rails into its position and lifted up using hydraulic jacks onto the A-frames on either side. The arches are simply massive. Together with the roof, the whole weight is 2,800 tons. That's the weight of 18 empty jumbos. You can see the struts joining them together. This gives them a lot of rigidity, stiffening the whole roof from sway from wind loads pushing the building sideways. The hangars are inclined from the arch down to the joints here where they meet the roof frame. This is to keep them in line with the frame, which runs straight along the building. The hangars distribute the weight of the roof along the arch, just like the spandrels on the stone arches we saw at Nîmes. This arch is much longer and flatter than the rounded arches at the Pont du Gard or the pointed Gothic arches in Cologne. And you can see there are no buttresses on the outside of the building. So how does this arch stand up? It's an ingenious solution. The arch is like a bow on its side, and the roof frame acts as the bowstring, tying the ends of the arch together. Here at the end, the force down the arch meets the support, and the arch tries to push outwards. This steel link ties the arch to the roof frame, which you can just see sticking out of the building. The push outwards creates a pull in the roof frame right through the building. This is the bowstring effect, which allows the arch to sit on these flat bearings here without a buttress. We're right underneath the roof here and right on top of the jumbos. You don't often get to see them from this angle. It's the workhorse of the world, the 747, and it gets refitted every 6 to 10 years. This one's nearly finished. Another 5 days and it'll be off to the paint shop. The roof frame itself is made up of trusses which run along the building and across. This is one of the two which are connected to the hangars up above. Being this big gives the roof the stiffness it needs to support the cranes which carry engines and other heavy equipment around down there. This is one of the access platforms underneath the roof. Can we go down, please? Get a great feel for the size of the hangar here. The hangar in Hamburg is a prestigious building, a centerpiece for Lufthansa's technical operations. It's a structure in the public eye, a showcase of engineering confidence, clearly visible to the passengers in planes taxiing by. The great space could have been bridged using more standard beams and trusses, but the result would have looked like an industrial shed. The arch, as always, has a natural beauty. The arch is a pure and simple form. As we've seen at the Pont du Gard in Cologne and here, it derives its strength from its shape. That shape has evolved over the centuries as new materials and our understanding of its behavior have developed. As well as a glorious past, the arch has a great future. In our next programme, we explore a 19th century masterpiece by Isambard Kingdom Brunel, the Clifton Suspension Bridge. We admire the magnificence of the vast new Storebelt Bridge in Denmark and enjoy the slender elegance of the Swiss Bay Bridge in the Czech Republic.